Hello everyone, welcome to the screen recorded lectures for Advanced Mechanics of Solids. So these are some special lectures arranged during the COVID-19 situation. I hope everyone is staying safe, taking all precautionary measures. If you remember, I had discussed earlier while our classes were going on that I would be discussing a couple of relatively easier topics near the end of the semester. So here we are. So the topic that we're going to discuss will be relatively easier than the earlier topics. I'm not going to say that this is easy by any way, but it is definitely easier than the previous topics, particularly because we are not going to take recourse to any of the variational formulations that we had been using earlier. So we'll be basically building on the concepts that we had learned during our undergraduate days. So the first topic, one of these relatively easy topics, is the unsymmetric bending of beams. All right. In certain textbooks, this particular topics is also referred to as skew bending of beams. So unsymmetric or skew. Okay. The moment we hear this topic, the name of this topic, unsymmetric bending of beams, the first natural question which should come to our mind is that if we are going to study unsymmetric bending of beams, then does it mean that all this while, all throughout our undergraduate days and during the first half of this course when we were studying the bending of beams, were we really studying the symmetric bending of beams? The answer to that question is yes. We had been studying all along the symmetric bending of beams. So this topic is something definitely new, but we are going to build on previous concepts. So what is different? What is the unsymmetric part here? So let's look at that first. In a very, very qualitative fashion, we'll develop the mathematical framework a little bit later. So going back to our undergraduate discussions, what we usually did back then was to consider a beam in this fashion. So we always drew the beam like this. In order to keep the picture simple, I will avoid drawing the supports, but I hope you all understand that this beam is not just hanging in air. There are definitely supports here at this end and at this end. I'm not going to draw it. Okay. So what we usually did was to consider some kind of loading. The most common was some kind of a point loading like this. There could be more than one point load, of course, or we considered some kind of distributed loading like this. It's not necessary that we have uniformly distributed load, but just to keep things simple, I'm drawing it as uniformly distributed load. Now, from the front view of this diagram, no question of symmetry or unsymmetry appears, but it will appear if we consider the cross section of the beam under consideration. So if we look at the cross section from this end, the most common cross section that we had been considering during our undergraduate days was a rectangular cross section. So it was something like this. This was the most commonly considered cross section. Now, immediately by looking at this cross section, we can identify that it is a doubly symmetric cross section, meaning that both about the horizontal axis, meaning something like this, as well as the vertical axis, this particular cross section is perfectly symmetric. Now, the symmetry that I mentioned uh, as far as our undergraduate studies was concerned, has definitely to do with this symmetry of the cross section, but it also has to do with the nature of the loading that was used. So if I draw a three-dimensional version of this diagram, what it will look like is something like this. So let's have our beam like this. So here we have the rectangular cross section. Now, as I mentioned earlier, this is definitely a beam having a cross section which is doubly symmetric. But it is also important to note that for the kind of formula that we are used to be applying from our undergraduate days, the loading that we used was supposed to be something like this. So suppose we had our y-axis in this fashion and the z-axis in this fashion, where we note that the y-axis coincides with the vertical axis of symmetry of the rectangular cross section, and the z-axis coincides with the horizontal axis of symmetry of this rectangular cross section. So the origin actually lies at the centroid of this rectangular cross section, and we will discuss in more detail about the centroid and centroidal axis later on. Now coming back to the load, what is important to note here is this particular distributed load that I have drawn here. It is not just arbitrarily placed on the top of this beam, rather it is arranged to be loaded in this fashion. So the load is acting vertically downward, but it is also passing or it is coinciding at this end with the y-axis, that is with the vertical axis of symmetry. So this load is very much vertically symmetric for this particular beam. So this was the symmetry that we were talking about from our undergraduate days. So let me write this down clearly. This thing, this is the case of symmetric bending of beams. So when we want to talk about the unsymmetric bending of beams, what is different? What is different is that we have to consider two possibilities. The first possibility is that the doubly symmetric cross section that we are considering here, this remains. So even though we consider unsymmetric bending of beams, the cross section itself remains something like this. It's still perfectly doubly symmetric, but the loading is no longer like this. So if we load the beam through some uniformly distributed load or some kind of distributed load or some kind of point load, but it is not arranged to be passing through the vertical axis of symmetry of the beam, then we'll no longer have the symmetric bending of beams. So that is the first possibility. So let me go to the new page, and draw that clearly. the cross section is symmetric, just like before, but loading is unsymmetric. So we can easily depict that in a three-dimensional configuration in this fashion. So we again draw the rectangular cross section. This is our beam. We again draw our y-axis and the z-axis. Which coincide respectively with the vertical axis of symmetry and the horizontal axis of symmetry of the rectangular cross section, but this time the loading is in a different way. So you can see here clearly that the loading makes a certain angle with the y-axis. We still have a uniformly distributed load. I have chosen it that way. I might as well have a point load, but this is no longer coinciding. The line of action of this load is no longer coinciding with the vertical axis of symmetry, and certainly not with the horizontal axis of symmetry also. So this is very much a case of unsymmetric bending. The next case, the second case of unsymmetric bending that is possible, is where the cross section itself does not have any symmetry. So we'll have something, a cross section which is somewhat of this fashion, some kind of an irregular geometry. So if we have a beam like this, no matter what kind of loading you impose on this is going to be an unsymmetrical bending. All right, so what we are going to do is to study this second case. We are going to study this second case. That's because if we can develop the mathematical framework to cover this particular case of unsymmetric bending, this is the more complicated case compared to this one, then this first case can easily be derived from this second case. And as a special case of that mathematical framework, the symmetric bending of beams can very well be derived also. So if we can have a framework for this, everything is covered. So that's our plan. But before we can launch into the direct development of that plan, of that mathematical framework for the unsymmetric bending of beams having some kind of an irregular unsymmetric cross section, we need to briefly brush up on some of the very preliminary concepts associated with bending of beams. So what we want to discuss first of all is the concepts associated with centroid, centroidal axis, principal axis, and the all-important topic of neutral axis. Okay. So let us go to a new page and start discussing these preliminary concepts. So suppose we have a cross section like this, which obviously doesn't have any symmetry, and we set up our coordinate axis arbitrarily in this fashion. Then refer to this to these coordinate axes, our centroid will be calculated in this fashion, or the coordinates of the centroid will be calculated in this fashion. So this is the definition of the centroid coordinates. The y coordinate will be given by this formula, integration y dA by a, where this capital A denotes the area of cross section, area of the cross section. The z coordinate of the centroid will be given by this formula, and you can immediately see that this is not too different from the way that the center of mass is defined. The only difference is that the density is not present here on the right hand side. Okay, now let's say that as a result of this calculation, the y bar and the z bar, they come out to be somewhere here. So let's say this is y bar, z bar. Now suppose next what we do is we consider this very same cross section, but we shift our coordinate axis, the origin of our coordinate axis, to this y bar, z bar. So what I want to do is to consider an axis, a pair of axes like this, y dash, z dash. Note that the origin of this y dash, z dash coordinate system lies at y bar, z bar refer to the yz system. Now in this y dash, z dash system, what do you think would be the formula for the centroid coordinates? It will be nothing but 0, this, and 0, this. I believe this should be clear to everyone. So I could have written this on the left hand side as y dash bar and z dash bar, but I know that that will be nothing but the centroid itself, and since the centroid is a property which is directly connected with the geometry, so it has nothing to do with the choice of the coordinate system. So the y dash bar and the z dash bar are nothing but 0 and 0. All right. Now what is important to note here is that this particular coordinate axis, y dash and z dash, because they pass through the centroid of the cross section under consideration, they will be referred to as centroidal axis. Now we must not have any impression that this y dash must be parallel to the original y-axis and the z dash must be parallel to the original z-axis. We might as well have a pair of centroidal axis which is like this. So y dash, y double dash, z double dash are also centroidal axis. Okay, when we develop our concepts later on, we will be repeatedly referring to centroidal axis and the centroid. So it is important to remember this particular page. The next topic that we'll brush up is has to do with principal axis. So let's go to a new page. Before we can discuss principal axis, we have to first of all recap the concept of the second moment of area, or rather the definitions of the second moment of area. In our undergraduate textbooks, this particular term, the second moment of area, is sometimes referred to as the moment of inertia. I'm sure most of you know this already. So just to recap, for a cross section which looks like this, some arbitrary cross section, and where the coordinate axes are like this, sorry, I don't need the dash here, I'll just keep that as y and z. The second moment of area can be of three kinds. The first one, Iy, is defined as integration of z square dA integrated over the entire area. Iz defined as integration of y square dA, and Yz, Iyz, which is defined as integration of yz dA. So these are all definitions. So we might as well denote it clearly like this fashion. So this colon with the equal to sign, it denotes that these are definitions. We are choosing to define it like this. I personally do not like this term, the moment of inertia, very much. Not particularly fond of this, because the moment we write something like inertia, I have an intuitive feeling that this must have something to do with the mass. But please note here that this is purely a geometrical property here, this Iy, Iz, Iyz, just like the centroidal concept, the centroid concept. This is a purely geometrical concept. It has nothing to do with the mass. It has a direct resemblance with the moment of inertia that we study in high school physics, but it is certainly not that. Anyway, for historical purposes, many textbooks still refer to these things as moments of inertia. Now, to go back to the question of what are principal axes, we have to understand first of all that the values of Iy, Iz, and Iyz depend very much on our choice of the y-axis and the z-axis. So if we keep on maybe rotating this y and z axis, maybe shifting the origin of this thing, the values of Iy, Iz, and Iyz are definitely going to change. Now, if it so happens that we choose our y and z axis in such a fashion that the value of Iyz turns out to be 0, then in that particular case, the y-axis and the z-axis will be referred to as the principal axis. So let me repeat that. As we keep on changing the orientation and the position of the y-axis and the z-axis, the values of Iy, Iz, and Iyz will keep on changing. If we end up with such a orientation and position of y and z axis such that the value of the Iyz is equal to 0, then in that particular case, the y-axis and the z-axis will be referred to as the principal axis. So let me write that down quickly. Now, it is interesting to note that when we have such a situation that Iyz is equal to 0, it also so happens that the values of Iy and Iz take on extremum values. So one of them is a maximum, the other is a minimum. So it is of course possible to prove this mathematically, but we are not going to go down that route. You can draw some analogy with the two-dimensional state of stress that we studied during our undergraduate days, and where we said that if we have a state of stress given by sigma xx, sigma yy, and sigma xy, the principal stresses would be given in that situation where the sigma xy is equal to 0. In a similar fashion, here also, when Iyz is equal to 0, the Iy and the Iz, they correspond to principal axis. So as a little thought exercise, try to think about what would be the value of Iyz for a cross section like this, where the axes are in this fashion. For a cross section like this, where the axes are like this, and in this particular situation. The next preliminary concept that we are going to brush up is the extremely important concept of neutral axis. So let me go to a new page and discuss that. So I believe we all have a fairly good idea of what the neutral axis is. Nevertheless, considering the extreme importance of this concept, let us write down its definition in words. So the axis in a cross section along which the bending stresses are 0. It is very, very important that we note that this is the axis, the neutral axis, the axis in a cross section. So what do we mean by this? So let us go back very briefly to the consideration of a symmetric bending of beam, and note that the picture is somewhat like this. So we have the beam cross section, in this way, and the neutral axis in this way. Let me draw that again. This is a little bit tilted still, so I'll try that again. Okay, I think I'm happy with that. I'll try to draw the stress distribution on this, exactly following from what we learned during our undergraduate days. So okay, so the picture that I am thinking of is where the cross section of the beam, which is above the neutral axis. So if this dashed line represents my neutral axis, the part which is above it is under tensile stress, or if I imagine that, in which case the bottom part would be under compression, or if I consider the other way around, that the top part is under compressive stress, then the bottom part would be under tensile stress. So let me draw the latter. So the top part I denote by a compressive stress, and the bottom part by tensile. Okay, I'm fairly happy with that picture, and we of course understand that the beam is here. So this picture is relatively a simple picture, although I took a fairly long time to draw it. There's a fairly simple picture that we have from our undergraduate days, and this is the case of a symmetric bending of beam. I think I didn't draw one line here. So as I was saying, this is the case of symmetric bending of beams. Nevertheless, even from this consideration of a symmetric bending of beams, we can learn a lot. The first thing to note is that this neutral axis, as the definition says, this axis is in the cross section. This is very important to note. This is my cross section, this is my entire beam, but I am only concerned with a particular cross section when I'm talking about the neutral axis. So some textbooks, they denote the neutral axis to be something like this. So when you are looking at the beam from the front, the projection of this neutral axis, as you consider different cross sections along the beam, along the length of the beam, that is what they refer to as the neutral axis. But that is wrong. I don't want to consider that as my neutral axis. So I'll remove this dashed line. So this dashed line, that is within the cross section, that is my neutral axis. Okay. Now, this is a very elementary concept when we are talking about the symmetric bending of beams. But even when we go up to unsymmetric bending of beams, we can build on this concept. How? So we have already seen that in the case of unsymmetric bending of beams, especially the second case that we are going to consider, when not even the cross section will be symmetric, and certainly the nature of the load will not matter if the cross section of the beam itself is unsymmetric. Even in that difficult case, there will be an axis passing through or in the cross section where the bending stresses will be zero. It will not be such a nice horizontal line, but it will be there. There will be a certain line in the cross section where the bending stresses will be zero, and that will be the starting point, or that will be the connecting bridge between the concepts, between our undergraduate concepts and the concepts that we're going to develop now. So in connection with this neutral axis, there's a very interesting point. It's such a nice and clean point that we can almost write it like a theorem. And this theorem says that as long as a beam is subjected to pure bending, and this is very important, so as long as a beam is subjected to pure bending, the neutral axis will always pass through the centroid of a cross section. So let me write that down. So this little statement can very easily be proven starting from the consideration that what we are considering is pure bending, which is to say that there are no axial forces acting on the beam. So no axial forces. So connected to this point, under pure bending, we have zero axial forces. And that means now it will be fairly easy for us to understand what we have just written if we quickly refer to the diagram on our left. So that is this diagram. But the good thing about this statement is that it will be true even if we consider unsymmetric bending. But first let us understand it here. So let me just quickly denote my coordinate axis. So see, what I have done here is I have written it as y-axis, and the z-axis is coinciding with the neutral axis. Now, because we are accustomed to seeing this picture, we may say that what is the point of trying to prove this, because we can clearly see that the neutral axis is very much in a symmetric position in this diagram, which means that the neutral axis is surely passing through the centroid, and we have taken the z-axis also to be coinciding with this, so everything is perfect here. But as I said, what we are going to develop here will be also be pertaining to a very general situation. So let us pretend, for the sake of a deeper understanding, that this neutral axis is there, but we do not know that this neutral axis is passing through the centroid of this rectangular cross section. So we are going to pretend that this neutral axis here is not going to pass, or we do not know that it is going to pass through the centroid of this rectangular cross section. So there is some value in trying to prove what we are going to prove here. Okay, so the next step of the proof is where we use the famous Hooke's law. Sorry, I don't want this color. To write the sigma xx as Young's modulus times epsilon xx. Now, because we have studied applied elasticity in the previous semester, and we have grown accustomed to writing the sigma xx in a fairly complicated fashion, where we may have dependence on epsilon yy and epsilon zz. But you please note that here, when we are considering the bending of beams, we are implicitly working under the limitations of the Euler-Bernoulli beam hypothesis. And within that Euler-Bernoulli beam hypothesis, we do not allow for any strains along the y direction or the z direction. We are only considering strains which are normal to the cross section. So we are only considering the possibility of length changes along the longitudinal axis of the beam. Next, as an oft repeated step, we are going to represent the epsilon xx in terms of y and the radius of curvature. So I believe I have already discussed this particular result in class earlier. So we need to put a minus here. So epsilon xx is equal to minus y divided by capital R, where R is the radius of curvature of the beam under consideration. Okay, so the Young's modulus is a constant. Under pure bending, the radius of curvature does not change. So what we can do is we can take the Young's modulus and the R out of this integration, and what we'll have is basically this. And this shows us that what we wanted to prove has actually already come out. So let's take a let's recap what we have actually done here. We wrote the sigma xx using the Hooke's law as Young's modulus times the epsilon xx. We represented the epsilon xx in terms of the y by r, and then we obtained this thing. Now, one may question, how does this show that the neutral axis is passing through the centroid? Well, you see, here in this diagram, referring to this diagram, the y is being calculated referred to the z-axis. So the y coordinate is the y coordinate of any point which is here. So this is the direction y. That means that the z-axis, and please note that the z-axis is coinciding with the neutral axis, so this thing is actually has to pass through the centroid, because you see the y dA integration of y dA equal to 0. The integration y dA is nothing but very much a part of our definition of the centroid. So if you remember it from earlier, we had written it like the y coordinate of the centroid was defined like this. So if integration y dA is equal to 0, it means that because capital A is not 0, the y bar has to be 0. And the y bar has to be 0 means the centroid is actually lying on the z-axis, which means that because the neutral axis is coinciding with the z-axis, because the neutral axis is coinciding with the z-axis here, the centroid must lie on the neutral axis, or the neutral axis is passing through the centroid, which is what we wanted to prove. All right. Now this was in reference to the case of symmetric bending, but this same concept will apply very much even if we consider unsymmetric bending of beams. So as I had said earlier, even if we have a completely irregular cross section with no symmetry whatsoever, we can have a bending of beam. That will of course be an unsymmetric bending of beam, but in that case also there will be a neutral axis along which the bending stresses will be 0, and it is guaranteed that that bending stress, that neutral axis will pass through the centroid of the cross section, provided we are considering a case of pure bending. So with these considerations, this brush up of the preliminary ideas under our belt, we can launch directly into a discussion of unsymmetric bending of beams and the development of the formula associated with that. So we'll start doing that from the next page. Okay, so we'll consider a general cross section like this, and we'll set up coordinate axis in this fashion. So this is my y-axis and this is my z-axis. What I will note here very importantly is that because this is an irregular cross section, there is no symmetry here, and which means that as you can clearly see also, this y-axis is certainly not any vertical axis of symmetry. The z-axis is certainly not any horizontal axis of symmetry. These are just some arbitrarily chosen mutually perpendicular coordinate axis. But one may question that is there any specific choice about this origin? The answer is yes. What I want to do is I want to place this origin at the centroid of this cross section. The reason is I want that I want the neutral axis, wherever or however it may be oriented for this cross section. I don't know how it will be oriented right now, but it will be there, I know that much. I just want to guarantee that the neutral axis will pass through this particular origin. And because in the previous page I had just proven that whether it is symmetric bending of beams or unsymmetric bending of beams, the neutral axis is guaranteed to pass through the centroid. So if I choose the origin of my coordinate axis y and z to be at the centroid, the neutral axis is guaranteed to pass through the origin of this coordinate axis also. So what I will do is I will just denote the neutral axis in this fashion. And what I will do is I will also orient a new coordinate axis z dash along this neutral axis. So maybe this color. I'll call this as z dash, which means that my y dash will be like this. That follows naturally. So what is the motivation here? Why am I doing all this? So to get the motivation, we'll quickly take a look at the previous page. So here you note that first I had this nice doubly symmetric rectangular cross section. I knew that the neutral axis would be oriented in this fashion, and what I did was to orient or place my z axis along the neutral axis, and then I proved whatever I wanted to prove. But the key point to extract from this simple or simpler case of symmetric bending is that the z axis here is lying along the neutral axis, which means that the sigma xx that I denoted here, so these red arrows, they denote the sigma xx. Here the sigma xx is tensile in nature, it will be positive. Here it is compressive in nature, it is negative. But somehow I want to have my expression of the flexure formula that will have a direct connection with how the z axis is oriented here. So the key point to note here is this: the distribution of sigma xx here, it is arranged in a linear fashion about the z axis. So what I mean here is the very simple picture which we are all accustomed to seeing from our undergraduate days, where repeatedly we used to draw diagrams like this, that we consider the cross section to be like this, and we drew our stress distribution like this. So you note that whatever I have drawn just here is nothing but the front side projection of this three-dimensional picture. I repeat, whatever I have drawn here is just the front side projection of this more complicated picture in 3D. And you note that this particular point is just the front end view of the point which denotes the neutral axis. Now I want to import this idea directly to the case of unsymmetric bending. So going back to the next page, that is exactly what I have done here. I have first of all denoted the neutral axis by this yellow colored dashed line. I have then arranged for one coordinate axis, the z dash, to be oriented like this. The y dash follows naturally from there. So my hope is that the bending stress that will emerge on this cross section, the sigma xx, which will be pointing either out of this plane or into this plane, will have some sort of linear distribution, and this is very, very important, so I repeat it. The sigma xx that will emerge from this cross section and which will be denoted by arrows pointing either into the plane or out of the plane, those sigma xx will have some sort of linear distribution about the z dash axis. They will have some sort of linear distribution about the z dash axis. Why is that hope having some sort of basis? It is having some sort of basis because if the beam of which this cross section is a part, if that beam is subjected to pure bending, then forget about the y-axis and the z-axis. Surely there will be some fibers of the beam which will be in tension and some fibers of the beam which will be in compression. And because we are considering pure bending of beams, it is natural for us to expect that there will be some flexure formula which will give us a distribution for the, or some sort of answer for the sigma xx. Right now we don't know what that answer is, but we only want to develop some kind of intuitive or physical feel for that sigma xx. And the physical feel that we develop is that it will have some kind of distribution about this z dash axis. So for example, if the part which is lying above the z dash axis, so let's say this part, suppose if that is in tension, then the sigma xx will be pointing outward. The arrows denoting that sigma xx will be pointing out of this, and if the correspondingly this lower part, the part below the z dash axis, that will be in compression, and the arrows will be pointing into the board here. Okay, but that is only a very qualitative picture. How can we develop a more quantitative picture for this? So for that, what we'll have to do is a little bit of algebra. So first of all, what we'll do is we will consider a generic point on this cross section. A generic point which will be denoted somewhere here. So let's say we take this point to be, let's maybe use a different color, so maybe somewhere here. Now refer to the y-axis and the z-axis. This point that we have just taken will have the coordinates as y comma z. I repeat, the coordinate points for this particular point that you have chosen would be y comma z. Now how can we write this in terms of something involving the y dash and the z dash? Okay, so you will see the motivation for that in a few minutes. So what I want to do first of all is I want to drop a vertical from this point. So Okay, I've dropped a vertical from this on the z-axis. Next, I recognize that refer to the z-dash axis, this will have a coordinate z y dash here. So this length that I have just drawn, this will be y dash. Now this entire length, I understand, is y. This is referred to the YZ axis, the red colored axis, and this one is referred to the Y dash Z dash axis. Now what I will do is I will denote the angle between Z dash and Y by beta. So this angle will be beta. So if that is beta, this will also be beta, this will also be beta. Okay, so what I want to do right now is to represent my y in terms of y dash and z. That can be easily be done by considering, first of all, this triangle. So we are considering this particular triangle first of all. So my y will be composed of this length and then this length. So first of all, to denote this particular length, I will use my y dash. So that will be y dash divided by sine beta. Next, for this little part, I'll use my z, and that will be z by tan beta. So what I'm doing here is to recognize that this much is my z. So this being beta, this length will be given by z by tan beta. The moment I have this, I can immediately write my y dash as y sine beta minus z cos beta. So we multiply throughout by sine beta, and we transpose the z term to the left hand side. So we express the y dash in terms of y and z. So what is the use of that? Well, as I was mentioning earlier, that we have some sort of an intuition that the sigma xx, the bending stresses, would have a linear distribution about the z dash axis. So we understand It is very important to note that we are considering pure bending, and the bending stresses sigma xx will have a linear distribution about the z dash axis. Basically means that the sigma xx will have a linear distribution about the neutral axis. The z dash axis is actually coinciding with the neutral axis here. Now, although we understand that this will be a linear distribution, but we don't exactly know what that form of the linear distribution is. So that is one of the big challenges here, to understand what that exact form is. So to keep things general, what we'll do is we'll just write it like this: sigma xx is equal to k y dash. So this particular form ky dash represents that the sigma xx is linear about the z dash axis. What we don't really know is what is the value of this k. But it is quite meaningless to talk about the bending stresses without first clearly denoting what the pure bending is. So what we'll do here is to denote the pure bending in terms of a bending moment. So let's use this color. So we'll denote the bending moment, but in terms of its components along the z-axis and the y-axis. So it's like this. Let me draw one line. I'll make it disappear to reduce the clutter. What I want to do is I want to denote the vector representation of my bending moment in this fashion. So this kind of a vectorial representation means that the bending moment is, and I wish I could actually show you how I'm curling my fingers, but I'll try to describe it as best as I can. So what I'm trying to do here is I have taken my right hand and I am curling my fingers, or I'm wrapping my fingers about this orange colored doubled arrow. So I'm curling my fingers about this stem, about this line. I'm curling my fingers around this, and I'm making my thumb point along this one. So when I do that, that gives me the sense of the bending moment. But I don't want to keep it like this. What I want to do is I want to resolve this in terms of its components along the z-axis and the y-axis. So that will be something like this. Okay, this is not too bad, so maybe I do not have to make this orange colored double arrow disappear. So but I don't have to consider this. So because I've already taken the components, I do not have to consider this. I will only consider this component along the z and this component along the y. So this is mz and this is my. So this is the loading that is inducing the bending stresses, sigma xx. So now that we have this picture in our hand, what we can do is try to express the mz and the my using the sigma xx. So let's see how we can do this. So while we do this, we will first be using the y-axis and the z-axis, because of course the my is oriented along y and the mz is oriented along z. So what we'll do is we will first of all write down the one-line expressions of mz and my and work on that in the next page. So first of all, the mz. Now, without worrying about the signs, what I need to write here is that in terms of the bending stresses, the mz will be brought about by this expression. So what I'm doing here is the sigma xx times the dA gives me the elemental force, and that elemental force multiplied by the y here, so sigma xx multiplied by the dA gives me the elemental force, and that multiplied by the moment arm y gives me the moment. That's fine, but I have to be a little bit careful about the sign now. You see, when I'm considering the mz, so this is my mz, and when I'm considering this expression, I understand that the x-axis is pointing out of the plane here. So the orientation of my x-axis is like this. So this denotes that the x-axis is coming out of the plane. So this is my x-axis. I have my x here. Now, because my x is pointing out of the plane, by sign convention, my sigma xx, the positive convention of sigma xx, would also be out of the plane. Now, if I consider an arrow representing the sigma xx, which is anywhere on this cross section, and I take the moment using the y moment arm, then and this is the part where I really miss teaching live in class, because I wish I was able to show it by using my hand and my fingers, by curling it in the proper way, but we'll try to make the best of what we have. So I take my sigma xx pointing out of the cross section, and y is the moment arm. So the y sigma xx here, it will give me a sense which is opposite to the mz. So what I mean is this. So let me see if I can make this picture clearer, somewhat clearer. In a three-dimensional sense. So suppose I consider this to be my beam, and These are my y-axis and z-axis. My mz is pointing like this, and my sigma xx is well, the positive convention means that this is my sigma xx, this is my sigma xx. So anywhere that I'm drawing, it is following the sign convention, the positivity sign convention. So if I consider this kind of a moment arm, so this is my y, so you understand that if I shift this arrow here and take the vector product like this, this clockwise sense of the turn from this moment arm to the sigma xx means that I would have to curl my fingers of my right hand in such a fashion that my thumb would be pointing along the negative z axis. So please mark my words carefully. If I'm taking the moment using my moment arm y, which is this, and turning my fingers in such a way, turning the fingers of my right hand in such a way that it's going like this, then the thumb of my right hand is pointing in the negative z axis, which means the moment that this thing by itself is inducing is pointing along the negative z axis, which means that this is opposite in sense to the given load, the given bending moment mz, which means that there must be a minus sign in front of this. Now let's see if we can write down the expression for my. So again, without caring about the sign convention, let me first write down in terms of the sigma xx. So this time, since I want to denote the my, I have to use my z as the moment arm, and now I worry about the sign convention. So what I'll do is I'll erase this thing here, and I'll read out the picture to get a clear-cut idea about for my my. Okay, so I understand that my my is pointing like this. So this is my my, and my sigma xx, just like before, is like this. Now the moment arm for this about the y-axis would be given by this z. So this is my z. Now if I shift it like this and I curl my fingers and I curl the fingers of my right hand in this sense, then the thumb of my right hand would be pointing along the positive y-axis. I repeat, for this sigma xx, for calculating the moment about the y-axis, so this is the y-axis, I need my moment arm to be this one. So this is the z. I shift this z here, and then I curl my fingers from this moment arm into this sigma xx, such that the thumb of my right hand is pointing along the positive y-axis, which means that I do not need to put any minus sign in front of this. This is just correct with positive sign. So to make things explicitly clear, this is positive. So this expression on the right hand side, whatever the sense of the moment here is this, it is perfectly matching with the given load, the given bending moment my. So there is a plus sign here. So all that we have to do is to substitute this expression of sigma xx equal to ky dash here in this expression, and sigma xx equal to ky dash in this expression, and finally to express or to substitute the expression of this y dash from here, y sine beta minus z cos beta, and that will set us up for some algebraic simplifications. Okay, so we'll do that in the next page. So the first thing that we need to write is mz is equal to minus sigma xxy dA integration. Okay, so this is just a repetition of what we wrote in the previous page. We substitute the expression of sigma xx, so that is ky dash and then we substitute the expression of y dash. So we check once more from the previous page. So this is the expression we need, y sine beta minus z cos beta. So this is k sine beta integration y square dA minus k cos beta yz dA, which means we can immediately rewrite this as k sine beta iz minus k cos beta iyz. Next, for my, we have sigma xx z dA so just as before, we substitute sigma xx is equal to ky dash. I'm not going to write that again. I'll directly write ky sine beta minus z cos beta times z dA, from which we have my is equal to k sine beta Iyz minus k cos beta Iy. We number our equations. This first one involving the minus mz as 1, and the second one, this m involving the my as 2, and then we simply divide 1 by 2 to quickly eliminate the unknown k. So we'll do that in the next page. So we simply divide 1 by 2. So we take a look at the previous page. So this is k sine beta Iz minus k cos beta Iyz, and this k will be eliminated. So this is basically just sine beta Iz minus cos beta Iyz. And in the denominator, we have from equation 2 sine beta Iyz minus cos beta Iy. So what we do simply here is to divide the right hand side throughout by cos beta to obtain tan beta Iz minus Iyz divided by tan beta Iyz minus Iy. Therefore, if we cross multiply the terms, what we'll get is minus mz tan beta Iyz plus mz Iy is equal to my tan beta Iz minus my Iyz. And from this we can collect the terms involving the tan beta. So this term on the left hand side, we'll take it here together with this one, so that will give us a tan beta common. So we can quickly write that tan beta will be equal to mz Iy plus my Iyz divided by let's see, mz Iyz, and this term on the right hand side myiz, right, myiz. That's it. Okay, so what is this giving us? You see, if we just take a quick look at our initial picture, so this horrible messy looking picture, and if we just focus on this beta, so what was this beta? You see, this beta denoted the angle that the z dash axis was making with the y axis, but we had chosen the z dash axis to coincide with the neutral axis. Therefore, the beta is the angle that the neutral axis is making with our coordinate axis y. I repeat, beta is nothing but the angle that the neutral axis is making with our y. Now you see the situation that we are in. It was our choice to orient the y and the z axis in this particular fashion. So we are in complete control of y and z. We know about this. What we didn't know was the orientation of the neutral axis. So our way of depicting the neutral axis was rather an ignorant way of denoting it, basically because we did not know the value of this beta. But now you see what has happened. As a result of all our manipulations, of all our algebraic manipulations, we have expressed the beta, of course the tan beta, in terms of things which we completely know about. First of all, we know about the value of mz because that is given to us. It is the z component of the bending moment that is given. My is the y component of the bending moment that is given. So both mz and my we very much know. Furthermore, because we have complete knowledge about the cross section, about the geometry of the cross section, and we have actually chosen ourselves the y axis and the z axis, it is very much within our power to calculate the value of Iy, to calculate the value of Iyz, and to calculate the value of Iz. So all the things that are present in the numerator and all the things that are present in the denominator are completely known to us. Therefore, as a result of our algebraic manipulations, we now are in possession of the knowledge of beta, which we had earlier not known. Therefore, right now what we have managed to do is find out the orientation of the neutral axis referred to one of our chosen coordinate axis. So now that we know about the neutral axis, about the orientation of the neutral axis, can we perhaps go one step further and ask ourselves if it is possible for us to find out an expression for sigma xx. So let us take a quick look back at our expression of sigma xx. You see, our sigma xx was here. The thing which we did not know about sigma xx was k, and you see that we really did not know about the y dash also, because y dash was dependent on the orientation of z dash, and we really did not know about the orientation of z dash back then, because we did not know about the orientation of neutral axis, and the z dash is coinciding with the neutral axis. But now, because we are in complete knowledge of the value of beta in terms of known quantities, so we know about z dash, which means we know about y dash. So the only thing that we do not know is k. If we can find out k, we can find out the value of sigma xx. So can we find out the value of k? So let us look at a different page here. So if we come back to equation 1 or equation 2 and substitute the expression of tan beta here, that can easily be done. Then we can find out either from equation 1 or from equation 2 the expression of k. So after finding out the expression of beta in terms of tan beta, we can find out, it is very much possible to find out the expression for k. The only difficulty there is the fairly long algebraic manipulations that we have to deal with. But in terms of of the ease or the simplicity of the steps, nothing could be simpler. So all that we have to do, and I'm not going to write down this in detail, I'm just going to outline the steps here. So let me go to the next page and write this down. After we know about beta, we can go to equation 1 or equation 2 to find out the expression for k. Once we do that, it's not very difficult to find out the expression for sigma xx. So without going into any of the fairly long algebraic manipulations, let me just give the answer here for sigma xx. So this is the answer for sigma xx. So this is my times yz minus ziz minus mz ziyz minus yiy divided by this entire thing divided by iyz square minus iyyiz. Now a couple of points to note here is that maybe 3 points. First is that this expression of sigma xx is basically just a very general version of the very familiar flexure formula that we have been studying all along during our undergraduate days. So this is a general or a generalized flexure formula. Which is applicable for unsymmetrical bending. And of course we can extract the answers to some very to much simpler cases directly from here. For example, if we have the special case where the entire bending moment is oriented along the z-axis, so we don't have the value of, or we have my equal to 0, and this becomes considerably simpler. A more important simpler case is when the y and the z axis are chosen to be such that they are principal axis, and we have already learned earlier that in such a case where the y and z axis are principal axis, the iyz will be equal to 0, and in that case this formula becomes much simpler. So you can try to find out that is iyz equal to 0. This will become much simpler. You can also try to find out the well-known expression of the flexure formula for that we learned in our undergraduate days. Maybe, for example, for a very or for a doubly symmetric rectangular cross section. Those are fairly easy things to do. So with this, we have more or less covered the important things from the theory part of unsymmetrical bending. The next topic that we will discuss is shear center, which will make use of this generalized flexor formula in some form. All right. Thank you very much.